Picture a long, straight road stretching left and right forever. We mark a special spot right in the middle and call it 0, that's home base. Every other number is just a position on this road. Positive numbers like 1, 2, 3 are steps to the right, and negative numbers like -1, -2, -3 are the same number of steps to the left. We call this road the number line. It's the simplest map of all numbers, with 0 as the starting point. Imagine you're playing a game where you can move left or right, but what you really care about is how many steps you've taken from the start, not whether you went east or west. If you walk 3 steps left, you're just as far from home as someone who walked 3 steps right. That how far idea is called distance, and on the number line it's always a positive number. You can't be negative steps away from something. In calculus, this idea of distance from 0 becomes the absolute value, and it's the key to measuring how close two numbers are, which is the heart of limits. To find the distance of any number from 0, you simply count how many steps it takes to get there, ignoring whether you went left or right. Mathematically, we just drop the minus sign if there is one. So the distance of 5 is 5, and the distance of -5 is also 5. We have a special symbol for this, 2 vertical bars around a number, like a little fence. It's read as the absolute value of x, so the absolute value of -7 is 7. Think of it as a number's size or the magnitude, its distance from the origin, always non-negative. Let's use this idea in a real situation. Suppose the temperature outside is -4 degrees Celsius, that's 4 degrees below freezing. The weather report says it will warm up to 6 degrees Celsius. How much did the temperature change? We don't care about the direction, just the total gap. The distance from -4 to 6 is the absolute value of the difference, 6 minus a -4, which is 6 plus 4, giving 10. So the temperature changed by 10 degrees. Notice we used the idea of distance on the number line. From -4 to 0 is 4 steps, and from 0 to 6 is 6 steps, making 10 steps total. This same method works for any two numbers, just find the distance between them by taking the absolute value of their difference. We already know absolute value tells us the distance from 0 on the number line. Now we are going to write that idea as a precise two-part rule, called a piecewise function. It says, if the number is already 0 or positive, just leave it alone. But if the number is negative, we multiply it by -1, which flips it to the positive side. This is written with a big curly brace, showing one rule for x greater than or equal to 0, and another rule for x less than 0. So the whole idea is captured in two simple lines. In calculus, we need a watertight definition. Saying just make it positives is not precise enough when we start taking limits or derivatives. The piecewise definition tells the machine, or our calculation, exactly what to do for every single real number. It splits the number line at 0, so we can handle the positive side and the negative side separately. This is crucial later when we find the slope of the absolute value function, because the slope is different on the left and on the right. Without this two-part rule, we would be guessing every time we hit a negative input. Let us build this from the number line we already know. Imagine a point at +3. Its distance from 0 is 3, so the absolute value is just 3. The rule says if x is greater than or equal to 0, output x. That matches. Now imagine a point at -3. Its distance is also 3, but the number itself is negative. The rule says if x is less than 0, output -x, and -x means -1 times x. For x equals -3, -1 times -3 is +3. The minus sign in the rule cancels the minus sign of the number. That is why -x becomes positive when x is negative. It is not a mysterious trick, it is just multiplying two negatives. Let us see this on a graph. we plot y equals the absolute value of x. For x greater than or equal to 0, the rule says y equals x. That is a straight line going up to the right with a slope of 1. It passes through points like 1, 1 and 2, 2. For x less than 0, the rule says y equals negative x. That is a straight line going up to the left with a slope of negative 1. It passes through points like negative 1, 1 and negative 2, 2. Both pieces meet at the origin, 0, 0, forming a perfect V shape. The graph makes it crystal clear. The right arm is that leave it alone piece, and the left arm is that flip its piece. So the whole idea is that one simple V-shaped graph is built from two different linear rules, joined at 0. We already know that absolute value tells us how far a number is from 0. But we can use the exact same idea to measure the distance between any two numbers on the number line. If you have two numbers a and b, the expression a, b simply means the distance between them. It doesn't matter which one you write first, because distance is always positive. 5 to 2 is 3, and 2 to 5 is also 3. So a, b is a ruler that measures the gap between any 2 points. Why do we care about distance between numbers? Because in real life, we often need to say this value is within a certain range of a target. Imagine a machine part that must be 3 centimeters long, with an error of at most 2 millimeters. That means its actual length can be anywhere from 2.8 to 3.2 centimeters. We can write this compactly as x, 3 less than 0.2. This idea of a center and a radius is everywhere, in manufacturing, in statistics when we talk about margins of error, and in calculus when we define limits. It's the language of close to. Let's see how this center and radius idea works. Suppose we write x, 3 less than 2. The number inside the absolute value, 3, is the center. The number on the right, 2, is the radius. This inequality says, the distance between x and 3 is less than 2. To find all the x that work, we think, starting at 3, we can go left by up to 2 units, and right by up to 2 units. So x must be greater than 3 to 2, which is 1, and less than 3 plus 2, which is 5. We can write this as 1x less than 5. On the number line, this is an open interval from 1 to 5, with 3 right in the middle. The absolute value inequality is just a compact way to describe that whole interval. Let's solve a real engineering problem. A ball bearing must have a diameter of 10 millimeters. It's acceptable if the diameter is off by at most 0.05 millimeters. We can write this condition using absolute value, d, 10 at most 0.05. The center is 10, the radius is 0.05. To find the acceptable range, we split it, d, 10 must be greater than or equal to negative 0.05, and less than or equal to positive 0.05. Adding 10 to all three parts gives us 9.95 at most d at most 10.05. So any bearing with a diameter between 9.95 and 10.05 millimeters passes inspection. The absolute value gave us a precise, compact way to state the tolerance, and the number line picture shows it clearly. We already know absolute value gives the distance from 0 on the number line. Now we look at how it behaves when we do algebra inside it. There are 3 big rules. First, the absolute value of a product is the product of the absolute values. Second, the same works for division. Third, and this is the tricky one, addition does not split apart like that. Instead, we get the triangle inequality. And there is one more critical fact that trips up beginners: the square root of x squared is not just x. It is the absolute value of x. We will see why with a picture. Why do we care about these rules? Imagine you solve an equation and take a square root to undo a square. You might write the square root of x squared equals x, and then get only half the answer. That is a classic mistake. Knowing that it really equals the absolute value of x gives you both the positive and negative solutions. The product and quotient rules let us break down complicated absolute value expressions into simpler pieces. And the triangle inequality is not just abstract, it tells you the longest possible straight line distance between 2 points if you have to go via a third point. It is a guarantee that a detour is never shorter than the direct path. Let's build these from the idea of distance. The absolute value of a product, like 2 times 3, is the distance of 6 from 0, which is 6. But the distances of 2 and 3 are 2 and 3, and their product is also 6. This works because multiplying two numbers scales their distances from 0, and the sign of the result just depends on whether the signs were the same or different. The absolute value ignores that final sign anyway. Division works the same way, just scaling down. For addition, imagine walking. You walk a distance of A from home, then from there you walk a distance of B. Your final distance from home cannot be more than the total ground you covered, which is the distance A plus the distance B. That is the triangle inequality. Now for the square root of x squared. Picture the number line. Take -3. Squaring it gives 9, a positive number. Let's use the square root fact in a real problem. Suppose we have the square root of the quantity x minus 1 squared equals 4. A beginner might cancel the square and square root and just write x minus 1 equals 4, getting x equals 5. But that misses a solution. Instead, we apply our rule: the square root of something squared is the absolute value of that something. So the equation becomes the absolute value of x minus 1 equals 4. Now we use the distance meaning from earlier in this lesson. This says the distance between x and 1 is 4. So x can be for units to the right of 1, giving 5, or for units to the left of 1, giving -3. Both work. Check: 5 minus 1 is 4, square is 16, square root is 4. -3 minus 1 is -4, square is 16, square root is 4. The absolute value caught the hidden negative solution. You already know that absolute value measures distance on the number line. Now, we use that idea to build a neighborhood around a point. When we write x that is less than delta, we are saying the distance between x and A is less than delta. This creates a small open interval centered at A, stretching delta units to the left and delta units to the right. Think of it like a bubble around A. This bubble is the key to the formal definition of a limit, where we say f of x gets close to L whenever x is close enough to A. The delta tells us exactly what close enough means. Why do we need this neighborhood idea? Because in calculus, we constantly talk about things getting arbitrarily close to a value, but that's just words. To prove a limit rigorously, we need a precise game. The epsilon delta definition says, for any tiny vertical tolerance epsilon you give me around L, I can find a horizontal neighborhood of radius delta around A, so that every x in that neighborhood, except possibly A itself, has its f of x value within epsilon of L. The absolute value inequality x, A less than delta, is the tool that defines that horizontal neighborhood. It turns a fuzzy idea into a solid, checkable condition, which is essential for building all of calculus on a firm foundation. Now let's see how absolute value behaves in limits and continuity. The function f of x equals x is continuous everywhere. At any point A, as x approaches A, x approaches A. There are no jumps or holes. But at x equals 0, something interesting happens. The graph has a sharp V-shaped corner. a function is differentiable at a point only if it looks like a straight line when you zoom in super close. If you zoom in on the corner at 0, it never smooths out, it always looks like a V. From the left, the slope is -1, from the right, the slope is +1. Since the left and right slopes don't match, there is no single tangent line, so the derivative does not exist at 0. The absolute value function is continuous but not differentiable at its corner. Imagine you're in a car moving along a straight road. Your velocity is a smooth function, you slow down, pass through 0 as you stop, and then speed up in reverse. Your speedometer, however, shows the absolute value of velocity, it's always positive. As you pass through 0 velocity, the speed graph has a sharp V-shaped corner, just like the absolute value function. The speed is continuous, it doesn't jump, but at the exact moment you stop, the rate of change of speed is undefined. The speedometer needle's movement has a kink. This shows why continuity and differentiability are different ideas. A function can be perfectly continuous, like your speed, yet have a corner where the derivative breaks. So the whole idea is, absolute value creates a precise distance-based neighborhood for limits, and its own graph perfectly illustrates the difference between continuity and differentiability. We already know that the derivative of a function at a point is the slope of its tangent line there. Now we want the derivative of the absolute value function, f of x equals the absolute value of x. Picture its graph, it is a V-shape, with the point of the V sitting at the origin. For any x less than 0, the graph is a straight line sloping downward, so its slope is -1. For any x greater than 0, it is a straight line sloping upward, with slope +1. But right at x equals 0, the graph has a sharp corner, not a smooth curve. There is no single tangent line that fits that corner, so the derivative does not exist at 0. Why do we care about the derivative of an absolute value? Because in the real world, many quantities are defined as distances or sizes, which are always positive. Think of the distance between two moving objects, or the error between a predicted value and a true value. We often want to know how fast that distance or error is changing. The absolute value function captures that always positive idea. Its derivative tells us the rate of change. For example, if a car's position is given by x of t, the distance from a fixed point is the absolute value of x of t. The derivative of the distance tells us the speed at which the car is moving away from or toward the point, ignoring direction. To find the derivative, we start from what we already know: absolute value is a piecewise function. For x less than 0, the absolute value of x equals -x. The derivative of -x is simply -1. For x greater than 0, the absolute value of x equals x, and its derivative is 1. We can write this compactly as x divided by the absolute value of x, for any x not equal to 0. Check it, if x is -2, x over its absolute value is -2/2, which is -1. If x is +3, it is 3/3, which is 1. At x equals 0, the left-hand slope is -1 and the right-hand slope is +1. Since these do not match, the function is not differentiable at 0. Now let's use this to solve a concrete problem. Suppose we have the function g of x equals the absolute value of 2x minus 4. We want its derivative at x equals 3. This is an absolute value of a function, so we use the chain rule. The derivative of the absolute value of f of x is f of x divided by the absolute value of f of x times f prime of x. Here, f of x is 2x minus 4. At x equals 3, f of 3 is 2 times 3 minus 4, which is 2. The absolute value of f of 3 is also 2. F prime of x is just 2. So the derivative is 2/2 times 2, which equals 2. Notice that the vertex of this V-shape is where f of x equals 0, at x equals 2. At that point, the derivative does not exist because the slope flips sign. We already know absolute value gives the non-negative size of a number, ignoring its sign. Now we apply that idea to three real situations. First, error tolerance. If a machine cuts a rod meant to be 100 centimeters long, and it actually cuts it at 99.8, the error is the absolute difference, just 0.2 centimeters. Second, distance between two moving objects. If a car is at position A and a bike at position B, the gap between them is the absolute value of a minus b, no matter who is ahead. Third, total variation. Imagine tracking a stock price that goes up, then down, then up again. The total variation is the sum of all the absolute changes, measuring the whole zigzag journey, not just the net change. Each of these uses absolute value to measure a magnitude that must be positive. Why do we care about these applications? In manufacturing, a part that is off by even a tiny amount can break a machine. The absolute error tells us instantly if a part is within its allowed tolerance, like plus or minus 0.5 millimeters. For moving objects, like planes or cars, we need to know the exact distance between them to avoid collisions. Absolute value gives that distance as a single positive number, regardless of direction. In physics and calculus, the total variation tells us the total distance traveled by a particle that moves back and forth. The regular definite integral would give 0 if it returns to the start, hiding the real journey. Absolute value captures every bit of movement, which is crucial for understanding wear and tear or fuel consumption. Let's derive each application from the core idea of distance. For error tolerance, we have a true value, say A, and a measured value x. The error is simply the distance between them, which we write as the absolute value of x minus A. We say the measurement is acceptable if that error is less than a small tolerance epsilon. This is exactly the neighborhood idea from limits x must lie within epsilon of A. For distance between moving objects, imagine two cars with positions given by functions f of t and g of t. At any moment, the gap between them is the absolute value of f of t minus g of t. This works even if they cross paths, because absolute value always gives a positive distance. For total variation, we break a journey into tiny time steps. At each step, the change in position is delta y. We take the absolute value of each delta y and add them all up. Let's solve a concrete everyday problem. A factory makes bolts that must be 3 centimeters in diameter, with a tolerance of 0.05 centimeters. A worker measures a bolt and finds it is 2.98 centimeters. Is it acceptable? We compute the absolute error, the absolute value of 2.98 minus 3. That's the absolute value of negative 0.02, which is simply 0.02 centimeters. Now we check, is 0.02 less than the allowed tolerance of 0.05? Yes, it is. So the bolt passes inspection. Notice that if the bolt were 3.06, the error would be 0.06, which is greater than 0.05, so it would be rejected. This method works for any measurement, just take the absolute difference from the target and compare to the tolerance. The whole idea is that absolute value turns any difference into a simple, positive distance, letting us apply a single clear rule to every case.